I greet everybody at the presentation of the lecture course on biophysics. Biophysics, it is the term that is of two subterms. Bio, the meaning of this is the biological objects or biological objects systems, and physics, it is the fundamental study of the nature. So, to combine these, the object of study and the science as the tool to study this object are determined. The object of the study of the biophysics is the biological object, including the human body and its structures, and the science that studies that object is the physics. It is the biophysics. We will go through the 8 sections of physics, and that 8 sections of physics basics will be introduced to you to focus, to show you how physics can develops the models of the biological structures. But it is not the only to model the biological structures, as I said already, including the human's body structures. But also physics gives such opportunity as to quantify the human's body structures and human body as a whole, state and functions. What is the quantification? It is the measurement or calculation of the parameters that are absolutely objective and independent on the researcher, that estimate the state or a function of the human's structures. And this is the base for the researcher, particularly for the physician, to make objective conclusion about the state and function of the biological objects. Because what are actually measured? Physics parameters. And this is done by the equipment, by the devices. These are not dependent at all on the researcher. So that is why the biophysics is the study and quantification of the human bodies, structures, and the human body as the whole. It is just the definition of the biophysics that will follow at this lecture course. But it can't be avoided to add this lecture course with the presentation, with the demonstration of the nowadays medical techniques. Nowadays physics equipment that is employed in medicine. What are these? It is the ultrasonic scanning, it is the X-ray tomography, it is the magnetic resonance imaging, and so on. So, we should consider this lecture course as biophysics supported, aided with the fragments of medical physics. Let's start this lecture course. I greet everybody at the lecture on biophysics. The lecture theme you can take from the slide. It is Biomechanics, Principles of Analysis and Modeling of Human Musculoskeletal Structures Functions. The goal and objectives of the lecture are listed at the next slide. The lecture goal is biomechanics analysis and modeling of human musculoskeletal structures functions for the design of the human-robot cooperation controlled system. The lecture objectives are these: quantification of human musculoskeletal system mechanical performance based upon the biomechanics concept. And the objective under number 2 is biomechanics models implementation to make the design process of exoskeleton system economical and scientific. The lecture points are listed at the next slide. We start from the first point. It is the introduction. Biomechanics basic aspects. Here you can see the points of our way we follow at today's lecture. Number 1, it will be introduction, biomechanics basic aspects. Number 2, biomechanics analysis and modeling of human musculoskeletal structures functions. And at this point we'll stop at this: skeletal muscle contraction modeling and quantification, motion of limbs, bones modeling and quantification. Number 2, as the example of that biomechanics works for the medical, biological purposes. And number 3 point is biomechanics analysis and modeling of human lower limb during walking for exoskeleton design. And we finish with the summary and bibliography. Any physics phenomenon or process in the world is a natural series of changes taking place in space with the time. Mechanical motion is the same of its nature. It is the series of change of the body that is under study, position into the space relatively to other bodies surrounding this that is under study with the time. Mechanical motion is studied in by physics section, that is mechanics. The application of the mechanics to biological system is referred to as biomechanics. There are 2 domains of biomechanics: statics, that analyzes the bodies at rest or in uniform motion; dynamics, that is the study of conditions under which an object moves. The dynamics can be further discussed under kinetics concept dealing with the body motion and the forces that cause it to move, and kinematics describing body motion without regard to the forces that produce the motion. Let's start from the kinematics. In kinematics, quantitative discussions of motion are based on measurements and calculation of position, displacement, velocity and acceleration of the object that is moving. This simple example for the introducing this concept is the translational motion along straight line. in which every part of an object moves in the same direction and there is no rotation. The velocities and accelerations of all points of a body at a translational motion at a given time are the same. This allows study the only one body point translational motion, and this is just the first biomechanics model maybe suggested. It is the pointed mass that is investigated instead of the real whole body translational motion. In rotational motion about an axis, each body point is undergoing circular motion. The body, all points, circular path centers are at the rotation x. Axis O1, O2 is just that, considered as rotation axis. Rotation is described in terms of angular displacement in time, angular velocity, and angular acceleration. Angular velocity is the rate of change of angular displacement, and angular acceleration is the rate of change of angular velocity. The averages of velocity and accelerations are defined by the relationships shown at this slide. While kinematic concepts describe a segment of a body motion, the concept of kinetics gives us an idea of the force associated with that movement. When discussing the kinetic concept of motion analysis, we need to define force in biomechanics. Force is the simple way to represent load in biomechanics and can be defined as the action of one object to another. Force can be external or internal. In both cases, force is interpreted as the quantitative measure of the interactions between the objects. External forces either pull or push on the body that occurs from sources outside the body. Internal forces are those forces that act on the structures of the body and are generated by the body tissue. What should be mentioned as the result of the force subjecting the body? There are two possible, at least but not at last, results of the forcing the object. The number one, force can change the shape and the state of motion of an object, and force is characterized by magnitude, direction, and point of application. So, force is the physical parameter measuring the interaction between the objects, and these of three characteristics: magnitude, direction, and point of application. All these factors determine the effect of force on an object. There are multiple forces that act on an object, and it is possible to resolve these forces into a single resultant force that has the same effect as all other forces acting together. The process of combining these two or more forces into a single resultant force is known as the composition of the forces. Having understood what force is, it is essential to look into some of the laws guiding the force application. And what are the major laws? It is the Newton's 3 laws of motion. These are fundamental statements about the physical world. Newton's first law of motion, also known as the law of inertia. Inertia is the resistance of the body to change its state of motion. When there is no net force, firstly, an object at rest remains at rest, and secondly, an object in motion continues to move with a velocity that is constant in magnitude and direction. The example of an area in which the first law of motion is applied is in static analysis. Static analysis is an engineering method for the analysis of forces and moments produced when objects interact with other objects. This concept is applied in biomechanics for the estimation of unknown forces of muscle, for example, and joint reaction in the musculoskeletal system. Newton's second law of motion relates to the impulse of a force. This law states that a net force will act on an object to change its momentum by causing the object to accelerate or decelerate. It is also called the impulse momentum principle and has an array of applications in sport. Sports performance is concerned with the increasing and decreasing the speed of movement of human body or the sporting equipment. This principle leads to the improvement of the sport technique on how the amount of force can be applied for longer, for example, in shoot put. Analytical formula of the Newton's second law is shown here. Force equals to the product of the mass of the object moving and its acceleration. Newton's third law of motion may be represented as this. If one object exerts a force on a second, then the second object exerts an equal but opposite force on the first. One application of this concept is that an athlete will be able to run faster on a concrete surface compared to a sandy surface due to the opposing ground reaction forces that are required to propel the body. The quantity that indicates the ability of the force to cause rotation is called the moment of force or the torque. So, when we talk about translational motion, the cause of this motion is the force. But when we talk about rotation, it should be another parameter that causing the rotation kind of motion. It is the torque. It is the measure of the force to initiate, to set the body into rotation. The torque depends on the force, the distance from a point on the axis of rotation to the point where the force acts on the object, and the angle. This illustration you can see, and this illustration is accompanied with the equation quantifying the force torque. The direction of torque is given by the right-hand rule and indicates the axis about which rotation will tend to occur. When we talk about translational motion, the influence of the object is measured by the object mass. Mass, actually, it is the quantitative measure of the inertia, the ability, the property of the body to resist, to change its motion. But when we talk about rotation as the kind of the mechanical motion, the measure of the object to resist, to change the rotation motion is different. It is the moment of inertia. Is the name given to rotational inertia, the rotational analog of mass for linear motion. It appears in the relationship for the kinetics of rotational motion. The moment of inertia must be specified with respect to a chosen axis of rotation. For a point mass, the moment of inertia is just the mass times the square of perpendicular distance to the rotation axis. That point mass relationship becomes the basis for all other moments of inertia, since any object can be built up from a collection of point masses. The relationship between the net external torque and the angular acceleration is of the same form as Newton's second law, and it's sometimes called as the Newton's second law for rotation. It is not a general relation as a linear one, because the moment of inertia is not strictly a scalar quantity. The rotational equation is limited to rotation about a single principal axis, which in simple cases is an axis of symmetry. Now please take this table as illustration showing, demonstrating the rotational linear parallels of parameters nomenclatures. And finally, for mechanics option, it is the statics. It is the study of the forces acting on an object that is in equilibrium or at rest. Our discussion of statics is based on an idealized object. It is model number 2. We consider it is the rigid body. An object extended in space that doesn't change its size or shape when subjected to a force. Objects such as human bones are often rigid enough so that their deformations at standard conditions of motion are negligibly small. So, in some cases, we can use physics model as pointed mass. This is very helpful and useful when the translational motion is discussed. In some cases, in cases of rotation, another model, physics model, rigid body, is useful and is considered. A rigid body will be in equilibrium of two conditions that are satisfied. So we talk now about statics. It is the study of the forces acting on an object that is in equilibrium or at rest. For this, there are two conditions required. The first, the condition that the net force is zero. For a rigid body, this condition means that the body as a whole are not accelerated or it is in translational equilibrium. The second condition for the rotational equilibrium is the absence of a net torque. This condition necessary for the equilibrium of a rigid body. This requires for the absence of rotation. When we look inside the human's body, particularly when we consider the musculoskeletal system, we can find the object linking with other. What are these objects? First of all, these are bones of the skeleton, and one more structure of musculoskeletal system is the muscle, skeletal muscle, that is just causing the motion of the passive fragments of the skeleton. These are bones. When we look at this configuration, bone, muscle, from the physics point of view, we can use and recognize one more physics model. It is the lever. So the skeleton and muscles may be considered as the lever system. When muscles develop tension, it pulls on bone either to support or to move the resistance of the applied load to a body segment. The muscles and bone are functioning mechanically as the lever. A lever is any rigid segment that rotates around a fulcrum. A fulcrum is a point of support or axis about which a lever rotates. A lever system exists whenever two forces are applied in a way that they produce opposing moments. Based on the arrangement of load, effort, and fulcrum, lever can be classified into first to third class. The mechanical advantage of the machine, that is the lever system, is defined as a ratio of the magnitudes of forces. Force F, it is the force exerted by the muscle, and force marked by the L symbol is the external force, or as it is named in biomechanics, it is the load. Movements of the human musculoskeletal system are accomplished by sets of bones, joints, and muscles that work together much like lever system. So, to say by that means we develop the human musculoskeletal system biomechanical model. It is the lever. A model is an object, plan, or theory that represents or imitates many of the features of something else. It is an attempt to represent reality. Biomechanical model is a representation of human mechanical system showing all force vectors and torques. Purposes of modeling are to increase knowledge and insight about reality, to estimate or predict variables of interest. Skeletal muscle isotonic contraction is the example demonstrating biomechanics modeling principle. This example reveals that the modeling is not the only presentation of human structures, but also it is the procedure of quantification of structures, states, and functions. This gives to the researcher invaluable, because it is objective information to make evidenced conclusion about human structures, states, and functions. First example, skeletal muscle contraction modeling and quantification. We will consider isotonic contraction, the type of skeletal muscular contractions in which the force applied by the muscle is sufficient to move to the load, and as a result the muscle shortens while muscle tension remains relatively constant. The contraction is called isotonic because the force remains constant during the contraction. The velocity of shortening remains constant as well. The relationship between the load and velocity is called load-velocity relationship, and this relationship is illustrated by the graph shown at this slide. What does follow from this graph? The greatest velocity of shortening is generated when the load on the muscle is zero. The peak velocity of shortening, an indication of the cross-bridge cycling speed. Cross-bridge, it is the moving element of the muscle. Biomechanics modeling of the skeletal muscle isotonic contraction is the example illustrating biophysics modeling basic principles. The skeletal muscle is modeled as the cylinder of the length L and the cross-section area A. It is shown as this simple diagram. So then the contracting muscle develops force causing the cylinder absolute shortening by delta L. The skeletal muscle isotonic contraction can be modeled as the mechanical work done by the force F at the displacement distance delta L. The force and the displacement are at the same directions. The equation for the force moving object at the same direction is this: work equals to the product of the force and displacement. The skeletal muscle isotonic contraction force can be expressed as the product of the force developed at the cross-section area unit. It is marked by F small letter, and the muscle cross-section area A. The force that is developed at the cross-section area unit is the constant equals to 40 Newton over centimeter squared for all skeletal muscle tissue. The relative shortening is one more muscle contraction characteristic. It is the ratio of the absolute shortening and the original length of the skeletal muscle. From this equation, absolute shortening may be expressed as the product of the original skeletal muscle length and relative shortening. Then the equation for the muscle mechanical work can be rewritten as this. Work equals to the product of these parameters. The product of the cross-sectional area and the original length of the skeletal muscle may be considered as the cylinder volume that can be expressed by the muscle tissue mass and the muscle tissue density. One more time, we can rewrite the equation for the mechanical work within the contraction period. The ratio of two constants F and density is the constant for the skeletal muscle tissue as well. The final equation for the skeletal muscle mechanical work may be expressed by that means. From here, two conclusions follow. The biomechanical modeling quantifies the isotonic skeletal muscle contraction and objectively reveals the direct proportionality of the mechanical work and skeletal muscle mass and its relative shortening. This biomechanics modeling result is the essentially scientifically supported base to solve medical problems, in particular the limbs prosthesis design. But the last requires much more complicated modeling procedure, including the experimental data recording and their computer processing. One more example of the modeling and quantification of skeletal muscular structures. It is the motion of limbs, bones, modeling and quantification. The tensed muscle exerts a force on the bone at the place where it is attached by the tendon. The bone muscle system acts as a lever with the joint as fulcrum. The muscle provides the effort and the load may be weight of the part of the body being moved or may include an external load. From the principle of moments, for a body in equilibrium, the torques of the forces should be equal and opposite in their signs. This may be expressed analytically by that means. Load times distance of load from fulcrum should be equal to the product of the force exerted by the muscle times distance of the effort from the fulcrum. Often the effort is applied closer to the fulcrum than the load, giving the system a mechanical advantage of less than 1. It is just this case. mechanical advantage is the ratio of the load and effort. This in turn equals to the ratio of the distance of effort from the fulcrum to the distance of load from the fulcrum. And this ratio, you can see from here, is less than 1. Consequently, the resolving force vertically reveals that the force from the shoulder bone at the elbow joint equals to 75 newtons. And this is just the example of the quantification of the function of the musculoskeletal structures. As it was mentioned already, the common anatomical lever in the human body is third class, and the reason is that the muscle insertion is usually close to the joint of action, thus the effort is usually between the fulcrum and the resistance, which is a third class lever. The design helps the body to gain motion and speed, and thus the human musculoskeletal system is designed for speed and range of motion at the expense of force. The modeling of a forearm as a lever with the fulcrum at the elbow joint reveals and evidence this statement. This as angular displacement, it is the parameter quantifying the motion of the forearm, angular velocity, one more parameter quantifying that motion, and linear velocity may be expressed. What for? For the point where muscle is attached to the forearm bones, and for the load, for the resistance. And you can see the linear velocity of the muscle contraction is much less than linear velocity of the motion of the resistance or the external load. And you can see that biomechanics, modeling, and quantification of musculoskeletal system gives the evidence of and reveals the reasons for the musculoskeletal system natural design. Bionics, or biologically inspired engineering, is the application of biological methods and systems found in nature to the study and design of engineering systems and modern technology. Lower limb exoskeleton have been a focus in the last decade, which are worn on the outside of humans' lower limb and able to follow the movement of human leg freely. For this, the gait analysis equipment should analyze the kinematics and dynamics of human lower limb more precisely. In particular, the motion mechanism of the three lower limb joints, that is, hip joint, knee joint, and ankle joint, should be analyzed, which is significantly important for the exoskeleton control. Analyze the kinematics and dynamics of human lower limb more precisely. In particular, the motion mechanism of three lower limb joints, that is, the hip joint, the knee joint, and the ankle joint, should be analyzed, which is significantly important for exoskeletal control. Except for the body motion, the muscles could play an important role in helping design a perfect actuator of exoskeleton. As we know, it is the contraction of muscles that drives the movement of skeleton around the joint. So, the biomechanics of the joint muscles are studied for better understanding of human motion, which is in favor of further optimized selection of exoskeletons, actuator and energy source. To reveal the relationship between human gait and muscles, the whole process is divided into two. Firstly, the motion of human walking is obtained by the human motion capture system, after which the dynamics of each joint, that is, torque of the joint, is studied by the gait analysis software. Secondly, the forces of the muscles driving such human walking are calculated by inverse dynamics after the capture motion data achieved by the above experiment are inputted into the muscle biomechanical simulation software. The motion capture system consists of 6 high-speed cameras arranged in the scene, 2-foot force plates on the pavement, a series of marked points pasted on the right positions of human body, and a computer for recognizing coordinate values of marked points and calculating the dynamics of each joint. One step during the process of experiment preparation is to set the markers by rule and line. 16 markers in all were installed on the body. Markers from 1 to 7 and markers from 8 to 14 are attached on the left and right lower limb separately. Marker 15 present sacral, and marker 16 was used to distinguish the left and the right. At the table you can see an example. Each body's segment was constructed by 3 markers. What are these? Ankle joint, shank and knee joint, thigh and hip joint. The idea of biomechanics analysis of human lower limb is to employ experimental data in the form of the dependence of the coordinate on time of the markers on lower limb. This reveals the real position of markers in the space. Combined with the ground reaction force measured by the foot force plate, the human joints torque during the gait subphases could be calculated based on the human dynamics model. Mathematical model of human is reconstructed by the multi-rigid body kinematics and dynamics based on Newton's Euler mechanics. In the experimental analysis, human working process are reconstructed by driving a three-dimensional virtual human using the data of joints angle alpha. As a result, the motion of the three-dimensional virtual human is very smooth, almost the same with the employee's real gait. Therefore, the measured result can be trustworthy. The natural gait would be roughly divided into the support phase and the swing phase. Compared with the swing phase, the support phase is more complex. According to the ground reaction force measured by the foot force plate, the support phase is divided into three sub-phases further. During the sub-phase 1, the heel of the swing leg strikes the ground and the two legs support on the ground at the same time initially, during which process the center of the gravity transfers from the later leg to the front leg gradually. During the subphase 2, only the support leg is on the ground and the other leg swings in the air. During the subphase 3, the original swing leg touches the ground again and the toe of the original support begins moving off the ground, preparing to enter the next gait cycle. Based on Newton-Euler mechanics, the mechanical equation is derived based on the balance equation of force and torque. According to the multi-rigid body theory, the human lower limb is divided into thigh segment, shank segment, and foot segment. As the example, for the foot segment, according to the Newton's second law, the force and torque of ankle are as follows. Biomechanics analysis of low limb motion is completed by the any-body modeling system, that is modeling and simulation software actually, that is used to analyze the mechanics of the live human body working in concert with the environment by computer-aided engineering. The any-body modeling system runs a simulation and calculates individual muscle forces, joint forces and moments, metabolism, elastic energy, intendance, antagonistic muscle actions, and much more for the further design of the lower limb exoskeletons. So, in conclusion, the human body is the result of natural evolution having a good movement forms and flexible driving mode. Biomechanics analysis and modeling activities, the kinematics and dynamics data about human lower limb by experiment. Biomechanics researches in details the principal muscle of knee joint under walk gait as human joint actuator, which is useful for bionics design of artificial limb and exoskeleton robot. Independently on that, the muscles' forces can't be measured directly. Let's consider that lucky case, that opportunity to do that direct measurement of skeletal muscles contraction. This is the example of the physics method implementation in medical practice. So, physics method of quantitative skeletal muscle contraction analysis is the dynamometry. And now please let's consider physics method of quantitative skeletal muscle contraction analysis. It is dynamometry. And what is the regime of the skeletal muscle is researched. It is the isometric contraction. It is the type of skeletal muscular contraction in which the force applied by the muscle is not sufficient to move the load, and as a result the muscle doesn't shorten, though its muscle tension or force of contraction increases. The resulting force development is the muscle twitch. If the frequency of stimulation is rapid, individual twitches become one continuous contraction, that is, a maximal force is generated. The frequency required to produce a maximum force is called a tetanic frequency, and the resulting contraction is called tetanus. Hand grip strength test is the kind of the dynamometry. That is physics method of mechanical force direct measurement. Is the procedure of measurement of the maximum isometric strength of the hand and forearm muscles group. Hand grip strength is important for any sport in which the hands are used for catching, throwing or lifting. Also, as a general rule, people with strong hands tend to be strong elsewhere. So this test is often used as a general test of the human strength. This slide illustrates this technique, this method, as hand grip strength test. One more may be suggested as the physics method of quantification of skeletal muscle contraction procedure. It is the assessment of maximal back muscle strength using the back dynamometer. Trunk muscular endurance testing with the low back problems have relative weaker extensor strength relative to their flexor strength. This assessment is illustrated by this slide. Assessment of maximal back muscle strength that uses the back dynamometer. And finally, let's summarize all that was said regarding biomechanics in context of modeling and quantification of musculoskeletal system function. Physical models are correctly used to quantify objective description of the mechanical movement of skeletal muscles and bone structures of the human skeletal. The human body is the result of natural evolution, having a good movement forms and flexible driving mode. Biomechanics analysis and modeling achieved the kinematics and dynamics data about human lower limb by experiment. Biomechanics researched the principal muscle of knee joint under walk gait as joint actuator, which is useful for bionics design of artificial limb and exoskeletal robot. Evidence-based parameters of the functional state of skeletal muscles are reflected by the physical diagnosis method dynamometry. And finally, here you can find the information resources to add to support this lecture. We finish. Thank for your attention.